Good morning and welcome to Tech 259 for Monday, March 1st. Today is going to be a review day where we'll talk about what's going to be on the exam on Wednesday and talk about how to study for the exam. But before we do that, let's review the last homework set that was over the material that we covered last Wednesday. So to do that, I will share my screen. Okay, here we go. Here is problem set number 12. This is the last problem set in the first half of the semester. It's the last problem set about thermal energy topics in the semester. So in the first question here, we have a pot of boiling water on an electric stove, and we're given the diameter. And we're told that the inside temperature of the bottom of the pot, the inside surface, is 108 degrees Celsius. And we're given the heat transfer coefficient. That's really nice because that way we don't have to calculate that. That will save us a lot of time. And we're asked, what is the heat transfer rate, assuming 1 atmosphere of atmospheric pressure? So what does that tell us? 1 atmosphere of atmospheric pressure? Well, it tells us the boiling temperature of the water. So if the water is boiling under 1 atmosphere of pressure, then it's going to boil at 100 degrees Celsius. That's the standard boiling temperature of water. So we have our basic equation for boiling that we talked about last time. The heat transfer rate for boiling is equal to the boiling heat transfer coefficient, H, times the surface area, times the delta T. This is the temperature of the surface minus the saturation temperature of the liquid. That's the temperature that it's going to boil at. And so we know our H, we're given it's 8,000 watts per meter squared per degree Celsius. We can calculate our area because we know it's 20 centimeters. So if the diameter is 20 centimeters, then the radius is 0.1 meters, which is 10 centimeters. So plug that into pi r squared. So square this and then take it times pi, and you get an area of 0.0314 meters squared. And we're told that our surface temperature is 108 degrees Celsius. And we know that our saturation temperature, because it says that we're at 1 atmosphere, then we know that our saturation temperature is just the standard 100 degrees Celsius. So in reality, if we wanted to be a little bit more accurate, in Bloomington normal, actually, the boiling temperature is not exactly 100 degrees Celsius. It's probably about 1.5 degrees less than that. It's probably somewhere around 98, 99 degrees Celsius, something like that. But it says it's 1 atmosphere of atmospheric pressure, so it's going to be 100 degrees Celsius. And so we just plug these numbers in. We plug in for the boiling heat transfer coefficient. We plug in for the area. We plug in for the surface temperature, subtract the saturation temperature, and keep your units, and then your units are going to cancel out. You got meter squared here that cancels out with meter squared here. You've got this term is going to have units of degrees Celsius, and that's going to cancel out with this degrees Celsius. And so the only units left are watts. And so that's always a good indication. If you're doing the problem and your answer comes out with the units that you expect, or reasonable units, then there's a pretty good chance that you did the problem correctly. So when you plug all that in, the answer that you get is about 2,010 watts, or about 2.0 kilowatts. Okay, that's pretty straightforward. The second question says we have a condenser, and that condenser has 50 tubes inside of it, each of which are 2 meters long with an outer diameter of 3 centimeters. All right, so that sounds like good information that we're going to have to use to calculate the surface area that condensation is occurring on. And we're told the outer surface temperature of the tubes is 20 degrees Celsius. The heat transfer coefficient, that's our H, is 4,000 watts per meter squared per degree Celsius. Once again, that's pretty convenient that it's given to us because that saves us a lot of work. We assume the condenser is operating at half of an atmosphere of pressure, and therefore it has a saturation temperature of 80 degrees Celsius. Remember, this is why we like to operate the condenser at a vacuum, because it decreases the temperature in the vacuum. So that increases the potential efficiency of the system. So anyway, that's why we have a saturation temperature that is below what we normally assume is the boiling temperature. So normally boiling and condensation occur at 100 degrees Celsius if we're talking about sea level or about 1 atmosphere. But since we have a lower pressure, condensation will happen at a lower temperature. So once again, what's the heat transfer rate? So our equation that we talked about last time for condensation is pretty straightforward, and it looks like this. The heat transfer rate due to condensation is equal to H, that's the condensation heat transfer coefficient, times the surface area, times the saturation temperature, minus the surface temperature. So once again, we're given H in this problem, which is super convenient. We have to calculate the area, and that's probably one of the most challenging things of this problem. It's not that challenging. So you have to think about it a little bit, and you have to think about what is the surface area of one tube, and then take that times however many tubes we have. So what is the surface area of the outside of a tube? Well, it's the circumference of the tube times the length of the tube. So that's pi d, which is the circumference, times the length. So pi times the diameter times the length will give us the surface area of one tube, then take that times the number of tubes. So that's in the number of tubes times pi d, that's the circumference, times the length of the tube. So we know there are 50 tubes, pi is a constant, the diameter is 0.03 meters, and the length is 2 meters. And so you plug that in and keep your units, and that turns out to be 9.42 meters squared. That's for all of the tubes in the condenser. We're told that the saturation temperature is 80 degrees Celsius and the surface temperature of the tubes is 20 degrees Celsius. So just plug all that in for the condensation heat transfer coefficient, the surface area, the saturation temperature, the surface temperature. Keep your units, your meter squared cancels out, your degrees Celsius cancel out, and you're left with about 2,260,800 watts, or about 2.3 megawatts. So this is a pretty good sized condenser. This is like a condenser used in a, well, I mean, maybe not quite utility size. You know, most utility scale condensers are going to be even larger than that. But this is a pretty good sized condenser. You know, this would probably be, to give you some scale, this would probably be, you know, about the size of a room in a house. Maybe not quite that big, but pretty close to like the size of the kitchen in your apartment or in a house, something like that. So it's a pretty good sized condenser there. And our last problem is near and dear to my heart. It's about a microbrewery. So this could be like the Distill Brewery that is not too far from my house. And I've taken a bunch of tours of the Distill Brewery. It's a great deal. They give you a souvenir glass, and they give you samples, and they give you a discount on merchandise if you take the tour, which is like $7 or something like that. So it's a really good idea to take the tour of the Distill Brewery if you're at all interested. So we've got this microbrewery, and it's cooling the beer wort. That's the name for beer before it's actually fermented into beer. And we're using a counterflow heat exchanger. We're given the inlet temperature of the beer, the wort. It's 95 degrees Celsius. We're given the specific heat capacity of the beer wort and the mass flow rate of the beer wort. And the other fluid that we're using to cool down the beer wort is water with a given specific heat capacity and a mass flow rate, and an inlet temperature and the outlet temperature are both given. Inlet temperature is 3 degrees Celsius, outlet temperature is 22 degrees Celsius. So what's happening is we're transferring heat from the beer wort to the water. And in the process, the water is heating up, and as it's heating up, it's taking heat away from the beer wort. So that's the whole idea. We're trying to cool down this beer wort. That's the idea. The only thing we don't know here is what is the outlet temperature of the beer wort. That's what we're trying to do. We're trying to cool that stuff down. So we have our equation for heat exchangers, which is really just an energy balance. So it says the heat transfer rate of the heat exchanger is equal to MC delta T, or MCAT, right? This is just MCAT for the cold temperature fluid. So this would be our water. And that's equal to the heat transfer out of the hot temperature fluid. So this is MC delta T, MCAT, for the high temperature fluid, which in this case is the beer wort. So it's worth noting that down, keep it straight in your head. What's the hot fluid and what's the cold fluid, so you don't mix things up. So in this case, the beer wort is the hot fluid, that's these variables, and the water is the cold fluid, that's these variables. And if you look at this for a second, we are given every single one of these variables except this one right here that says T sub H out. So that's the temperature of the hot fluid out. In other words, the outlet temperature of the hot fluid. All right, so all we really got to do is rearrange this equation to solve for this variable right here, because everything else is given. So I'll do a little bit of algebra here. I'm not going to plug in numbers right away. I'm just going to do some algebra on it and then plug in numbers. So the first thing I'm going to do is divide both sides by this term right here. And that leaves me with the T hot in minus T hot out right here. And then that leaves me with this still on the other side of the equation divided by these terms right here. So that gets me this. And now I need to do a little bit more because I really want to get this, the hot fluid outlet temperature. So I need to rearrange a little bit more to solve just for this term right here. So what I'm going to do is subtract the hot fluid inlet temperature from both sides, and then I'm going to take both sides times -1 because I don't want to get the negative T hot out. I want to get positive T hot out. So I got to subtract this from both sides and then take both sides times -1. And you'll get this equation where we've got the hot fluid outlet temperature on one side, and then we got everything else on the other side. So we have the hot fluid inlet temperature minus everything that was on this side of the equation. And that's divided by the mass flow rate of the hot fluid times the specific heat capacity of the hot fluid. So the good thing now is that we know all of these terms, they're all given to us. So all we have to do is plug in numbers here, keep your units. There's our hot fluid inlet temperature, our mass flow rate for the water, specific heat capacity for the water, delta T for the water, and we divide by the mass flow rate for the beer wort times the specific heat capacity for the beer wort. So keep your units here. It's kind of nice because this whole thing, kilojoules per kilogram per degree Celsius, it cancels out with this down here, kilojoules per kilogram per degree Celsius. So this all cancels out. The kilograms per second for the mass flow rate in the numerator cancels out with the mass flow rate in the denominator. And the only thing that we have left, we're going to have degrees Celsius minus degrees Celsius. So our answer is going to be in degrees Celsius. And what we're trying to find is the temperature of something. So that's a good thing. We want our final units to be in degrees Celsius. So you plug all these numbers into your calculator carefully. And the number you're going to end up with for this combination of terms over here is 56 degrees Celsius. So we're taking 95 degrees Celsius minus 56 degrees Celsius, which gives us 39 degrees Celsius. So the answer, the outlet temperature of the beer wort is 39 degrees Celsius, which is a heck of a lot cooler than it came into the heat exchanger. It came in at 95 degrees Celsius and it's coming out at 39 degrees Celsius. So it's done a good job. It's a pretty good design for cooling down the beer wort. All right, that wraps up our last problem set for thermal energy in the semester. The next problem sets are going to look very different than the problem sets that we've been doing these past month or two. So in the next video today, we're going to talk about the review of thermal energy and what's going to be on the first exam. So I'll see you in the next video.